Every automatic process loop ends at one device, the control valve. The DCS gives an instruction. The control valve executes it, throttling flow, pressure, temperature, or level in real time, automatically, without anyone touching a hand wheel. In this video, we open up the control valve and show you exactly how it works, from the valve body to the actuator, the fail-safe spring, the IP converter, and the positioner that makes it accurate. A control valve assembly has four main parts. The valve body carries the process fluid. It has an inlet, an outlet, and a seat ring inside where flow is throttled. The stem connects to a plug that sits inside the seat. The actuator is the pneumatic motor mounted on top. It converts air pressure into force on the stem. And the positioner is a smart device that ensures the valve actually reaches the exact position the DCS commands. The actuator uses instrument air to move the stem. Air enters the top diaphragm chamber. The diaphragm pushes down against a return spring. The stem, connected to the diaphragm, moves down with it, pushing the plug into the seat and closing flow. When air pressure drops, the spring pushes the diaphragm back up, lifting the plug and opening flow. The amount of air pressure determines how far the stem travels. The spring is not just for movement. It defines the fail-safe position. When instrument air fails, a compressor trips, a pipe breaks, the spring has only one job: move the valve to the safe position. If the spring closes the valve on air failure, we call it fail closed. A fuel valve must fail closed so no fuel reaches a burner if air is lost. If the spring opens the valve on air failure, it is fail open. A cooling water valve must fail open so cooling never stops if air is lost. Every control valve on a real plant is specified as fail open or fail closed, and that decision is made by the process safety team. The DCS speaks electricity. The actuator speaks air. The IP converter translates between them. It receives the 4 to 20 milliamp signal from the DCS analog output card. For every milliamp of input, it produces a proportional pneumatic output. For milliamps gives 3 psi. 20 milliamps gives 15 psi. If the DCS sends 12 milliamps, 50%, the converter outputs 9 psi. That air pressure goes directly to the actuator and positions the stem at 50% travel. The full control loop connects all these pieces. A pressure transmitter measures the process and sends a 4 to 20 milliamp signal to the Centum VP FCS. The FCS runs the PID calculation every 100 milliseconds. The output, a percentage, is converted by the analog output card to a milliamp signal. That signal reaches the IP converter on the valve. The converter outputs air pressure. The actuator moves the stem. The plug changes the flow. The pressure changes. The transmitter measures the new value. The loop repeats. Here is the invisible problem most technicians do not think about. Without a positioner, the control loop is open on the mechanical side. The DCS sends 12 milliamps. The IP converter outputs 9 psi. But friction in the packing gland, process fluid pressure pushing back on the plug, gravity on a heavy stem. These forces all resist movement. The valve may stop at 46% when the DCS asked for 50. The DCS does not know. It keeps sending 12 milliamps. The error stays. The positioner solves this. It has its own position sensor on the stem. It compares actual stem position to the commanded position and adds or removes air to close the mechanical error. With a positioner, the valve always reaches exactly where the DCS told it to go. The control valve is the final control element, the point where every DCS calculation becomes physical movement in the process. The body throttles flow. The pneumatic actuator converts air to stem force. The spring defines the fail-safe position. The IP converter translates milliamps to psi. And the positioner closes the mechanical loop so the valve always reaches the exact position the DCS commands. That is how a control valve works.